Dear students, Assalamu alaikum and welcome back to plant physiology course. In the previous videos we have discussed the concept of water potential, and mostly, as you have seen, we have taken hypothetical examples in which, for example, in the last video we have a beaker in which we have placed a container. Now this container has a membrane which is inelastic. So this is a hypothetical ideal membrane which does not stretch when water enters from the beaker into this container. Although it is semi-permeable, it allows the movement of water into this container. This is container A and this is container B. So water can move from A to B due to its water potential gradient, because it is high or less negative in container A, so it is less negative, and it is more negative or it is low in container B, so it is more negative, due to which water enters from container A to container B. But since this is an inelastic membrane, it does not allow the stretching, so entry of a very small amount of water inside this container B brings the whole system to equilibrium. That is, water potential both inside and outside becomes the same because of the development of turgor pressure inside. So this was our hypothetical example, or the hypothetical examples that we have seen in our previous videos. But we are discussing all this to explain the movement of water into a plant cell, into the plant. So when plant absorbs water, the situation is not like this. It is somewhat different. And that is, the plant cell is surrounded by, although a rigid wall, the cell wall, but cell wall is elastic to a certain degree, to some extent. That is, the volume of the cell increases when water enters. That is, the cell stretches, and obviously when there is a stretching of the cell wall, it means that there is an increase in the volume. And when there is an increase in the volume, for example, again let's draw, say this is a container and we have placed a plant cell in it. Now in initial state, this plant cell is flaccid. For example, this is its nucleus and this is the vacuole. Since water potential in container A, the psi W, is less negative, let's take a hypothetical value, say it is -20, and inside the cell, say it is -40. So obviously we have a water potential gradient from the beaker or this container towards the cell. Now this is the cell sap contained in the vacuole. So what happens? Water will enter from beaker crossing the cell membrane and the tonoplast into the vacuole. What will happen? That the cell will stretch. When cell stretches, because the cell wall is elastic to some extent, so when it stretches, certain amount of water enters the vacuole or inside the cell, and what it does, that entry of that water into it dilutes the cell sap, and this dilution means that more free water enters and it raises its water potential. So for a moment one can think that a plant cell is perhaps not obeying the water potential principles, or we cannot apply the water potential principles or the equation that we have studied in the previous videos. The answer is no. This is not the case. The plant cell obeys the principles of water potential, and the equation holds true as far as the plant cell is concerned. So let's see how it is possible. Say we have a container A with pure water. And that is its water potential is equal to 0. And then we have a plant cell in which the water potential is equal to minus 14. Now it can be any value, say it's minus 14 bars. Now as far as the equation in case of plant cell is concerned, so its water potential is equal to its solute potential plus pressure potential. Now it is minus 14 is equal to minus 14 plus 0, because this is a flaccid cell. We haven't yet placed it in pure water or in any hypotonic solution. So this is a flaccid cell, and its solute potential and water potential, they have the same value. Now what we do, that we place this particular cell in pure water with the water potential of 0. So what happens when we place, for example, this is a container and we have placed that plant cell. It is, for the time being, it is flaccid and its protoplast is in a shrunken state. So this is W psi W is equal to 0 and its psi W is equal to minus 14, right? So we have placed it. What happens, that cell absorbs water, water enters the cell through osmosis, and the cell stretches. When the cell stretches, there is a certain increase in the volume, and as we can see now, the cell has become fully turgid and there is a certain amount of increase in the volume, raising its water potential. So as you can see, its volume has increased. When its volume increases, its water potential is also raised. For example, its water potential has raised from minus 14 to say 12, minus 12, because of the addition of free water. When free water enters the cell, because it has 0 and it has minus 14, water will enter this cell sap or the vacuole of the cell. So its water potential is raised and it is now minus 12. When it reaches minus 12, as I just said, that the cell wall, although it is elastic, but it is elastic to some extent. It doesn't keep on expanding. So a point will come when the cell wall will no longer expand, or the cell will not expand, and there will be no further increase in the volume of the cell. So at that particular point, when the cell reaches its maximum volume, maximum size, or when it becomes fully turgid, so what will happen, that pressure will develop inside the plant cell. So now we have water potential that is minus 12, so will be its solute potential. It will be minus 12. So, and pressure will develop. So what we'll get as far as its water potential is concerned, that minus 12, and there will be a pressure development of plus 12 bars. So minus 12 plus 12, it will become 0. So its water potential will become 0, and it will equate, or it will equilibrate the water potential of the outer container, that is beaker. So its water potential has become 0, but not at initial state, which was minus 14 bars. Its water potential has become 0, but because of the addition of water, a certain amount of water has entered the cell, making its solution less negative or raising its water potential. So as we have just seen in this very simple example, that the equation of water potential is still accurate. It still holds true in case of plant cell, which absorbs certain amount of water, or there is an increase in the volume of the cell when it absorbs water. but whatever the case might be, finally its water potential becomes equal to the water potential of external solution because of the absorption of water. So this concludes our discussion of water potential. We have seen various aspects of water potential. In the next video we shall discuss inshallah imbibition and more about plant water relations. Thanks for watching and see you in the next video.